You got it. The natural log of 10 is basically that number. So, but why is that right?
Because when we do the soft practicing, we read all these exponentiations, and 10 is the number of classes that we have.
Okay, 10 is the number of classes. Okay, you're onto something. 10 is the number of classes. Okay. Right.
So with a model that doesn't know anything, you're probably going to predict 0.1 for all of your classes, right?
Okay.
Cover all your bases.
Right.
Give a good initialization, and so if you compute the log of 0.1, which is what you do in your cross entropy, because you're predicting 0.1 for the correct class, that is.
Yeah. So, and why is it 2.3 and not negative 2.3?
Well, cross entropy.
Because the negative in, right, the log of 0.1 is actually negative 2.3, but entropy has a negative in front of that. You guys got it, right. So the reason 2.3 is about the right number is because, yeah, like if everything's randomly initialized, then probably on average our model's going to spit out roughly uniform predictions across everything, and the cross entropy is going to say that's wrong, but 1/10, log of 1/10 is about 2.3. Yes. Okay, so you can sort of see like this number, like it makes sense. And this says if you get this number out, that would mean that probably a lot of things are going right for you. So your model is spitting out numbers. They're about evenly distributed. It's making uniform predictions. Your cost function is like doing its thing. Like everything's good. Yeah.
So is it just the cross entropy that's giving us the negative log probabilities, or will all loss functions kind of follow that general system? At least that we use in this class.
Just cross entropy. So
So
this
this
is
is assuming
specific.
cross
This is
entropy.
very specific to cross entropy.
Okay.
Okay. Yeah. Notice too that I said let's disable any regularization. Regularization would change this. Go ahead.
I forgot which piece of the whole process regularization is.
So remember, this is where we put a penalty on our weights, just to make them small. We penalize
Okay, so
big
yeah,
weights.
So the gradient, we moved in the direction of the gradient, and then we regularized so that it wouldn't blow up on us.
Yes.
Okay.
Well,
Well, no, so then
we just, part of our loss is we calculate the norm of the weights, and we just add that to our loss function. And so then when we calculate the gradient, it will want to drive the weights down. The regularizer wants to drive the weights to 0. But the model wants to drive the weights to whatever's useful for predicting things.
I don't see why disabling regularization is the thing that we're trying to do to make it so it just outputs.
Well, we just
Why
want to make
are
sure regularization isn't affecting the number that we get out. That's all.
Because that changes the loss function.
Because that'll change the loss function. Next slide. So if we crank up the regularization, say our lambda, the lambda parameter of our regularizer is high, then the loss should go
Oh, we're just making sure
up.
that increasing regularization makes the loss worse.
Right.
Okay.
Right. So you want to start at 0, just to make sure that the core loss is working, but then you want to crank up lambda. So these are just some tricks. So like fiddle around with the number and make sure that they're sort of doing the right, sort of about the right things and about the right times. Okay, yeah, tip, like try to overfit. Here's just a little more details about that. I have some graphs, let's see here. So here's, I think, some other just qualitative things you can do. So if you graph the loss over time, and you see something that kind of looks like this, going down, smooth and steady, that's good. So this graph on the left, that's pretty good. Over on the right, I've schematically diagrammed a few alternatives that you might see while training. So let's look at the yellow line to start with. So very high learning rate. Why would this happen?
Is this our training or validation loss?
This is training loss. Training loss. So if your learning rate is too high and you see things exploding, what's going on?
It's completely skipping over all the polynomials, just going all over the place.
Yeah, it's not overfitting. So this is training loss, not test loss. It's not, so imagine this is our loss surface. And you're over here. You calculate the gradient. It says go that way. And so you take a really, really big step. Like you take a step that's this big. What happens? You end up over here. So the loss goes up. So let's suppose now you say, okay, gradient's that way. Let's take another step. And it's a really, really big step. Go say over here. The loss goes up. So if your step size is too big, you'll actually bounce higher and higher and higher. Okay, what if your learning rate, why is this, let's look at this blue line, low learning rate. What's happening here? Yeah, it's like working, but just taking forever. So that's symptomatic of a low learning rate. You could probably turn it up and you'd be fine. High learning rate, what's going on here? Yeah, it's like your learning rate was, you like sort of made it to the valley, but you didn't make it all the way to the bottom of the valley because you're hopping over it. But if you have a good learning rate, it sort of goes down like this. Okay, so just as you're visualizing, this is some things you might see. And these are kind of the reasons, the qualitative reasons why you might see them. What if you see something like this?
Bad initials.
You got a plateau.
Plateau, yeah, could be. But this is the very beginning of training. This is the beginning of time right here.
You were kind of wandering around in the middle of nowhere for a long time, and eventually you started finding something good, and you went that way, and then you got stuck in a better middle of nowhere.
Okay.
I think
So the
that
learning
looks like
rate's
bad
too low.
initialization.
Yeah, kind of looks like you're saying maybe the learning rate's too low. You said initialization.
Because you got stuck.
I would definitely say, yeah, bad initialization. It's like somehow you initialized this thing so that there was like no learning signal at all. And eventually, thanks to all the hard work of all those deep learning people, they found what you meant. And they went ahead and like, did it for you. But if you had initialized something a little better, maybe you could have gotten rid of this initial plateau. So if you ever see plateaus at the beginning, bad initialization is a suspect. Okay, and then finally, so we've seen things, you've probably seen things like this. So let's imagine that this is our training accuracy here, and this is our validation accuracy here. There's a big gap. So if there's a big gap, what does that mean? This is classification accuracy here on the y-axis. Big gap means what? You can just read the slides and compare it back to me, that's okay. Overfitting, yeah. So, and if you're overfitting, what do? Well, you know, there's many different strategies. We'll talk about regularization in depth in our next lecture. If there's no gap, though, that might mean this, that maybe your model actually isn't powerful enough, and maybe you could add some more parameters, add some more layers, increase your model capacity.
Why does that tell you that?
Why does that tell us that? So how do we know that if we're not overfitting our models isn't powerful enough? Like the answer is actually, I think, in that sentence.
Well, just that's why we overfit at the beginning, because if we have enough parameters, there's enough space to essentially like memorize everything
Right.
it needs to learn.
Right. So it's sort of a tautology. It's like, if our model is powerful enough to overfit, then we should see a gap. If it's not powerful enough to overfit, then we won't see a gap. But if it's not powerful enough to overfit, then maybe it's not powerful enough to do what we want it to do.
So do we want to say small gap,
Small gap is good.
tiny gap?
Tiny gap. Yeah, question.
I was just gonna add, if you think about like, if you were trying to do learning and you have like a small number of items that you're learning about, I mean, basically you're not, it's not able to learn anything that's specific to the subset of data that it's you know, that's the training data. And so because you're not learning anything that's specific, you don't really have any guarantee that you're learning any, you know, enough that's general anyway. So it's until you get a little bit of specific data, then you know, like, okay, I'm learning more than there is to learn, so therefore I've learned everything that's important.
Right. Right. Yeah, thank you. Okay, we have 1 minute left. Yeah. Okay. We'll just end with this, which is, you just sort of want, this is again kind of a rule of thumb, the scale of your updates should be kind of approximately the right ratio with the weight, the magnitude of your parameters. And you don't have to worry about this too much because modern learning algorithms, like the optimization algorithms, like Adam, will take care of this for you. But if Adam isn't doing its thing, one thing you can check is how big are your gradients and how big are your parameters. And if there's a huge mismatch there, then things are probably going to break.
You're not updating them so much that they're totally changing all the time?
It's just weird. Like, you just want, no, it's more like if your weights are sort of numbers between 0 and 0.1, negative 0.1, and you calculate the gradients and you look at the numbers in the gradient, and it's like 2 billion, 3 billion, like, that's just bad. Like, something is wrong somewhere. Great. Let's call it good.